Hello, today we are going to design a PEB building. Let's start by creating a new project. I created and started a new project. I switch to the PEB tab and select type 510. Let our truss span be 30 meters. Our column height is 8 meters. Let's keep our axis spacing at 6 meters. Now, the program is creating our model. In this example, we won't have a column in the middle. I'm removing the middle column using the :/support command. To change the dimensions of the frame, I click the X-axis button and select the relevant frame. Then I press the Edit button. Let our ridge height be 2 meters. I want the purlin spacing to be around 1.5 meters. It's 1.38. The DCY parameter determines the beam start haunch reinforcement height. Let's make this part 0.8 meters. The DCX parameter determines the width of the column top. Let's make this part 1 meter. DRY is the height of the ridge point. Let's make this part 0.7 meters. The reinforced part will extend from the corner across 4 purlins. So roughly 1.38 meters times 4 is around 5.5 meters. The reinforced section in the ridge will continue for 2 purlins. I close this menu by pressing the OK button and update my model by pressing the Apply Changes button. Let's change the length of our building to be 60 meters. A building like this. The program placed the diagonals by skipping 2 axes. I can replace them if I want. But right now it's fine. Therefore, I am not making any changes. Let's look at the load section. There are several load codes in the program. I assume this project will be done in India. Therefore, I choose IS 875 as the load code. Let our roof covering be sandwich panel. At the bottom, it is possible to define a solar panel on our roof if we wish. However, we will not use solar panels in this project. Let's take a look at the snow load section. There is no snow load in the area where the structure is located. However, I still define a snow load of 15 kilograms per square meter. You can assume this load as a rain load. Let's move on to wind load. Since our building is in India, we will use IS 875 as the load standard. Let's say our building is located in a region where the wind speed is 44 meters per second. Therefore, I choose this region. Somewhere in this area. You can change the internal and external pressure coefficients from this section. I change it to +0.2. I'm assuming our building is inside the city. So I choose terrain category 4. I close it by pressing the OK button. We can add a point load to our roof with the Add Point Load command. We do not have a point load in this project. Let's take a look at the thermal loads part. The standard used here is EN 1991-15. Let the indoor temperature of the building be 25 degrees in summer. Let's set the winter internal temperature to 20 degrees. Let the highest temperature be 40 degrees and the lowest 10 degrees in the place where the building is built. We erected our building at 25 degrees. The long side of the building is in the southwest direction and the outer covering is light colored. In this case, our building will be exposed to a temperature difference of plus 22.5 degrees in summer and minus 10 degrees in winter. We will use these values in the calculation of the column braces. When we select India as the load code, the earthquake code automatically comes as IS 1893. Let our soil class be a poor soil, I choose Z4. Now let's choose the city where our building will be built. The program will automatically recognize the earthquake zone according to the city we choose. This is a moment frame system. Let's keep our live load participation coefficient as 0.5. The program has automatically assigned the loads we have defined so far to our model. Let's review the assigned loads. The most complex loadings in steel structures are wind loads. Let's take a look at wind loads first. The program calculated the wind loads acting on the roof and automatically assigned them to the relevant elements. It can do this in 4 different directions. You see the distribution of the respective loads on the roof purlins. We will use these loads in the calculations of roof and facade purlins. It automatically transferred these loads to the main frame system. These loads are used when static calculations of the main frame system are made. After this stage, let's move on to the secondary member elements. These elements are roof purlins and wall girts. If there was a crane or a mezzanine in our building, their secondary beams would also be our secondary members. As a steel structure design standard, the program includes Eurocode, Turkish Steel Structure Code, American Steel Structures Code and IS 800. Let's use the IS 800 first. Let's try the American code later. When cold-formed steel elements are used as roof purlins, the program uses N 1991-13 as the design standard. From this section, we can define sag rods for roof purlins. We can make purlins simple or continuous. If we wish to change the purlin sections using these arrows, we can use the same section for both purlins. I chose C200 to 15 purlins. And I use single sag rod. Now let's take a look at the wall girts. Wall girts are on the A-axis and B-axis of the building. You can change the number of wall girts from this menu, but I wanted to stay around 1.5 meters. Let them stay like this for now. C200 to 15 section seems to be sufficient here as well. Let's look at the other axis. There is no problem there either. The design of the secondary elements is finished. Now let's assign the cross-sections of the main frame system. Let's start with the columns. I select the columns at 0 and 30 meters. Facade cladding is sandwich panel. First, we choose the flange width and flange thickness of our profile. Let's choose 150 mm by 10 mm. Let's choose 400 mm as the height and 8 mm as the web thickness. If the height and web thickness we want are not in the list, we can define and use any section we want from this menu. As we can see, the section we defined has been added to the list. However, I want to use 408/150/10 section. I choose S355 as the steel grade. By pressing the Apply Changes button, our column sections are assigned. Let's assign the beams. Let's make the material quality of the beams S355 as well. Let our flange be 150 mm 10 mm again. The section I want to use this time is 410/150/10, but this section is not in the list. Let's create this section. My section is on the list. I choose 410/150/10. I misassigned the column sections. Let's fix this. Again I select the columns at 0 meters and 30 meters. I change the flange to 160 to 10. I will choose the height and web thickness as 400 to 10. This section is not on the list. Let's add. Now our column and beam sections are correctly defined. Let me show you the sections we have defined. The easiest way to see the cross-section of the building in the program is to look at it through cost analysis. I open XZ2 axis. The column section we selected is the column starting section you see here. We made the definition of the height value at the top of the column from the Edit Truss menu. When choosing the beam section, we chose the middle section. We have entered the heights at the beginning and end of the beam in the Edit Truss menu. Now let's do a static analysis of this system once. Static analysis complete. After the static analysis, the design menu opens on the right. Here we have seen that the cross-sections of the rod braces are insufficient. We need to change them. Let's take a look at the XZ axis. In this axis, my main columns are at 66% capacity. My main beams are at 75% capacity. In the earthquake regulation section, slenderness checks were made. We calculated with positive 0.2 wind load coefficient. We also need to calculate for negative internal pressure. For this, I first set the internal pressure coefficient negative 0.3 from the wind loads menu. I have to choose whichever option is more inconvenient. In the previous analysis, the columns had more higher ratio. For this reason, I have to calculate according to positive 0.2. I correct the pressure coefficient to positive 0.2. I correct again as positive 0.2. I know that the column braces are insufficient. I will use the same cross-section for all of the column braces. Here I will use a 30 mm diameter rod instead of a 20 mm diameter rod. I think this diameter will be enough. Here, instead of rods, we could use L or pipe cross-sections. Our rate dropped to around 1.1, but it was still insufficient. Let's take a quick look at the internal forces coming into these diagonals. First, let's take a look at the normal force diagram under earthquake load. We now see the axial force diagram. All of the diagonal members we've seen here have all been subjected to tensile forces. The elements that will receive the pressure force are excluded from the static calculation. It was made in static calculation according to thermal effects. When you click on the relevant element, we can see the incoming force. The braces in the middle receive a compressive load under thermal loads. Since the rod sections could not carry the pressure load, the braces on the side had to take the whole load. Let's go back to the capacity section. The capacity of our braces is over the limits. So let's change the cross-sections of these elements. This time, let's use an angle section instead of a rod section. For example, let's choose 60 mm 6 mm angle. Let's do static analysis again. "60 mm 6 mm angle sections gave close results with 30 mm rods. So I will have to use larger cross sections. This time I will use 80 mm 8 mm angle. I will use the same section on all axles. Instead of 60 mm 6 mm angles, I choose 80 mm 8 mm angles. Let's do static analysis again. My column braces are now running at 70% capacity. This is a pretty good result. Let's take a look at the main frame system. My columns and beams are running at 65 to 75% capacity. Let's make a change now. Let's try AISC 360-16, which is American code instead of the Indian code. Our braces are now running at lower ratios. This is due to the difference in load combinations in the American codes. The sections that are sufficient at 0.7 ratios in the Indian codes are not sufficient according to the American codes. This is due to the lateral buckling length. To fix this, we go to the Beam Lateral Support menu from the Model tab and add lateral support to the beams. Now let's add lateral supports at regular intervals. There is no problem with our braces. Let's look at the main frame. Now the capacity of our beams has been improved. However, our column capacity is still insufficient. To fix this, the pressure flange needs to be held in the columns, just as in the beams. To do this, let's move on to the model screen first. We will now define fly braces from the girts to the non-holded compression flanges of the columns, as in the beams. Let's go to the Secondary Elements tab and click on the girts. Now let's tick the girts as lateral supports for column button. As you can see, the program has defined lateral supports for the columns on this axis. Now let's repeat the same process for the other axis. The columns on both axes now have lateral supports. Now let's do static analysis again and see the difference. Static results on our long axis are the same. Now let's look at our other axis. As you can see, the column capacity ratios have decreased dramatically. Now let's take a quick look at how much steel we use from the cost estimation menu wherein after static analysis tab. I open the list by pressing the steel materials button. We used 28.56 kilograms of steel per square meter. Now let's take a three-dimensional model drawing and examine our column supports over the three-dimensional model. For this, we press the three-dimensional model button from our tab after static analysis and press the draw button from there. Now the program is preparing our three-dimensional model. This process may take a few minutes depending on the speed of your computer and the size of the model. Our model is ready. Now let's look at the lateral supports in 3 dimensions. As you can see, the program has placed lateral supports from the wall girts to the free flanges of the columns. Now let's close this place and define wind columns on the front and back of our building. To do this, let's first unlock static analysis and go back to the Model tab. We press the wind column button to define the wind column. We are at 0 meters coordinate. Let our sheeting type be sandwich panel. If you wish, you can choose different sheetings from this menu. I chose IP 300 as the wind column. Now I define the wind column by choosing the points I want. The points you selected will be displayed as red dots in the program. Let's choose the other part symmetrical. I chose points 3, 6, 10, 14 and 17. OK. Now let's define the columns at the 60-meter coordinate. I will choose a sandwich panel again as the coating type and make the columns symmetrical with the 0-meter coordinate. I will choose the same points again and make them symmetrical. Let's place our columns by clicking the Apply Changes button. Now let's define a gate between the axes A1 and A2. For this, let's click on the wind column button again, and press the Door Exist button next to the column we want to open a door for. As you can see, the program has defined our door. Door height is 5 meters as standard. Now let's do the static analysis for the wind column case again. Static analysis complete. The ratios on the y-axis have changed somewhat due to the wind loads coming from the front and the back face of building. Let's look at the x-axis. Now we have two static axes. The first is the wind column axis, and the other is the inner axis. Now let's take another look at our cost estimation menu. This time we used 31.89 kilograms of square meters of steel. The reason for the increase is the wind columns and purlins added to the front and back of the building. From this section, we can look at static model drawings. Here we can see the element and node numbers, the connection names and the lateral supported beam sections. Now let's look at the static drawing of the long side. We can also see the nodal points and bar numbers in the same way. Here you can see the column application plan. Let's take a quick look at the reports. You can access the detailed report of each element in the program. Reports are prepared in great detail and are supported by visuals. Let's pick and see some reports. I choose the loads purlin calculations and one variable section calculation as an example. Let's prepare the report by pressing the print button. The program started to prepare the reports of the sections we selected. This process may take a few minutes depending on the complexity of the model. Our report has been prepared. Now let's take a quick look at the details. As you can see, all the necessary details are given. In addition, loads are shown graphically. It is clearly written in the tables and codes used. Each parameter is clearly given. Complex wind loads are given graphically. Section features and formulas used in purlin calculations are clearly written. Calculations related to variable cross-section were made according to the selected regulation. All formulas used are clearly given with their references. In this way, the account report can be easily read and followed. You can save the report in PDF or image format and print it directly if you wish. This lesson is over. We will take a closer look at connection desing for the next lesson. Thanks for watching.